So last time what have we done? We have discussed now linear differential equations with constant coefficients, right? We have seen methods for determining the complementary function. How do you find the complementary function? You take the characteristic polynomial, you solve them, find the roots m1, m2, mr with their multiplicities k1, k2, kr, and write down the complementary function as monomials in x to the power j e to the power m k x, correct, where j runs from 0 to mk minus 1. And so you take the most general linear combination of these things and you get your complementary function consisting of n arbitrary constants. Now what is remaining? To find the particular solution. For that, that method that I described to you is the method of undetermined coefficients. And this method works for what kind of forcing function? When the forcing function is a linear combination of polynomial times exponentials, right? So in the right hand side is a polynomial times exponentials with linear combinations thereof. You can do this. What is the procedure briefly? You have to find an annihilator for the right hand side. So you let us say that yp is a particular solution. So qd of yp equal to rx, right? Now what do? You have found a annihilator, call the annihilator p of d and apply p of d to the entire equation. Then you get pd qd yp equal to 0. That is, yp satisfies a homogeneous constant coefficient ODE of a higher order, and you know how to solve it. So write down the full solution and cancel off those terms which already appear in the complementary function, and the remaining ones will appear with some coefficients a, b, c, d, etc. These are the undetermined coefficients. Now how do you determine these undetermined coefficients? How do you find the value of these undetermined coefficients? You substitute it into the original differential equation and compare the like terms and get these undetermined coefficients. This is the algorithm. So is it clear? Is the algorithm clear? The only thing you have to do now is to find annihilators suitably, and we have written down a list of annihilators. Yeah. Of course, once you find the annihilator of PD, then you get a higher order ODE. Then you have to write the characteristic polynomial of the higher order ODE. Already you have one factor QM. You have to find the second factor. That's correct. Yeah, once you find the annihilator, just find the roots of the annihilator. Yeah, that's true. Yeah, that's correct. Yeah, you won't do that. You don't do that. After all, you're going to multiply. Now, what you're going to get is in factored form only. PD into QD into YP equal to 0. So, what is the characteristic polynomial? PM into QM, correct? Right. So, QM is already there. But remember one thing. There could be common factors between PM and QM. So, if you just knock out the QM and just take PM, you're going to get the wrong answer. I say the best thing to do and the flawless algorithm would be to write down the full YP. YP satisfies a homogeneous linear ODE of a higher order. Write down the full solution and then cancel whatever is there in the complementary function.
We have already found complementary function in QM.
That is okay. Nevertheless, you have to write down the full YP. YP satisfies a higher order homogeneous linear differential equation with constant coefficients. The entire solutions has to be written down, and whatever is there in the complementary function has to be cancelled out. The rest contains the undetermined coefficients. That is the algorithm. There are no shortcuts. This is the algorithm. What I described just now is the algorithm. There are absolutely no shortcuts. Any attempt to short circuit this process, you run the risk of making mistakes. There are really no shortcuts. It's a time tested method. Right? So once again, let me go over this again. QDYP equal to Rx. You have found the annihilator P of D. Apply P of D to both sides. YP satisfies the homogeneous equation PD into QD into YP equal to 0. The characteristic polynomial for this is PM into QM. You have to write the full YP and then cancel out whatever is there in the complementary function. Right? So please don't try to short circuit the process. Is that clear? And this is a very important method, and most books, in fact all decent books will have a long chapter on this. And let me repeat, Giancarlo Rota in his very interesting article calls it the meat and potatoes of the course, the main course as it were, the main entree. So treat this as an important chapter and follow the instructions carefully. Okay. So now let us go to the next one, the Cauchy-Euler equation. This is the nth order linear ODE, this is the linear ODE an x to the power n dny by dx to the n plus an minus 1 x to the n minus 1 dn minus 1 y by dx to the n minus 1 plus etc. plus a naught y equal to Rx. As before, we shall take the Rx equal to 0 case first, that is the homogeneous equation first. You have to first solve the homogeneous equation, and after you solve the homogeneous equation, you will either apply the method of undetermined coefficients or method of variation of parameters. Method of variation of parameters is very clear and then nothing more need be said about it. Well, what is the method of undetermined coefficients in this case? We shall see. We shall see how to modify the method of undetermined coefficients to cover the Cauchy-Euler equation. Well, many books will tell you how to reduce the Cauchy-Euler equation to a constant coefficient equation. There is a simple transformation that will convert the Cauchy-Euler equation to a constant coefficient equation. I mean, you can consult those books, and I will not say anything further about that. It's there in almost every book. So I will completely not say I will completely ignore that procedure. That's an alternate method, a second method if you like. The method we are going to follow is very similar to the method that we followed earlier of taking a trial solution. So this time the trial solution that we are going to take is x to the power m. Why x to the power m? Because look at the differential equation. You are differentiating it j times and you are multiplying by x to the power j. Correct? So you see it's a degree preserving operator. X to the power j, jth derivative. The degree preserving operator. So when you apply x to the power j, dj by dx to the power j applied to x to the power m, you are going to get a multiple of x to the power m. Correct? That's the nice thing about the Cauchy-Euler equation. That is why the trial solution is taken to be x to the power m. So take x to the power m and you substitute. What are you going to get? What is the coefficient of what is the jth term? The jth term is a n minus j x to the n minus j dn minus j by dx to the n minus j y, or aj, you can look at aj x to the j jth derivative. Correct? It's aj x to the j jth derivative. So what is the jth derivative of x to the power m? M into m minus 1 into m minus 2 into m minus j plus 1. That's the coefficient. So that's what you see in equation 3.15. It is aj into m minus 1 into etc. m minus j plus 1. Summation j from 0 to n, that is your polynomial. That is called the indicial polynomial. And that equation 3.15 will be called the indicial equation. Correct? It's called the indicial polynomial because it determines the exponent m. The index m is what it is computing for you. So it's called the indicial polynomial. You are probably taught in your courses differential equations with regular singular points, the method of Frobenius. There again you encounter the indicial equation. That's the generalization of this. That procedure is simply a generalization of this. So I am using the same terminology, indicial equation. Right? No, it's a coefficient. Im is the coefficient of x to the power m after you substitute into the differential equation. You think about it, you will get it. It's very trivial. How this equation 3.15 comes about it, pretty trivial. Right?
What is m?
What was m in the constant coefficient case? The constant coefficient case, what was the trial solution? E to the power mx. So there again you can ask what is that m? No? So what are you supposed to do? You have to take this indicial equation Im equal to 0 and find the roots. Huh?
So what we will get is throughout x to m is small.
Right. Throughout you are going to get x to the power m common. When you substitute x to the power m, you are going to get Im into x to the power m. Exactly as it was the earlier case. Earlier case you got characteristic polynomial times e to the power mx. You are going to get the indicial polynomial times x to the power m. And so what should you do now? Take m to be a root of the indicial polynomial. Correct? So that's exactly what we are going to do now. For each root m naught of the indicial polynomial Im, we obtain a solution x to the power m naught. Just as in the earlier case, for each root m of the characteristic polynomial, we got a solution e to the power m naught x. Here, instead of the characteristic polynomial, we have the indicial polynomial. Instead of an exponential function, we have the power function x to the power m. The analogy is clear? Okay. So now, you should now worry about what happens when m naught is a complex number. How do I define x to the power m when m is complex? First of all, how do I define x to the power a when a is not a rational number? X to the power half is root x. Everybody knows that. So for a rational exponent, we understand what is the power of x. For an irrational exponent, even if you take real irrational, you can define it using the least upper bound property. But the problem is that now we are going to go a step further and go to the complex exponent. Then we will have to use the definition. The definition is there on the blackboard. X to the power m naught is by definition x of m naught log x. That is the definition of the exponential. So it is in some sense reducible to, it is in fact reducible to the exponential function. And how do I define the exponential function? As I said yesterday, it is a series, infinite series. E to the power z is 1 plus z squared upon 2 factorial etc. It is a power series with infinite radius of convergence. And so it defines a analytic function on the whole complex plane. That's the definition of the exponential function. So that's what we are going to, that's the definition we are going to adopt. M naught equal to a plus ib. Now, notice that in the definition itself, there is an exp of m naught log x. So now we have to worry about the range of x. X cannot be negative or 0. X is real. X is still real. And remember, look at the Cauchy-Euler equation. The top derivative term has an x to the power m sitting there. Right? It's not in normal form. And if you divide by that x to the power n in the differential equation, then you are going to get 1 over x, 1 over x squared, 1 over x cube all over the place. So the differential equation is not even defined at the origin. At the origin, the differential equation is not even defined. So origin is anyway out of the domain. And from the real line, if you remove the origin, it falls off into two pieces, the positive reals and the negative reals. And we shall work on the interval, which is positive real line. We will work on the positive real line only. So that's a thing on the bracket. I have made it very clear. We work on the positive real axis, namely x bigger than 0. Correct? Clear? Is the definition of x to the power m clear when m is complex? Alright. So now, I also told you yesterday that e to the power z1 plus z2 is e to the power z1 into e to the power z2, and the way you prove this is by multiplying the two power series together by taking their Cauchy product. And we have the theory of power series, in which you prove that when you take two power series, the Cauchy product converges in the intersection of the two disks of convergence. Both of them are power series at the origin. But here we don't have a problem because the power series converges everywhere, not a problem. So where the domain in which the Cauchy product will make sense, etc., doesn't appear. The thing makes sense everywhere. So the Cauchy product will also converge for all values of z1 and z2, no matter. You don't have to worry about, there are no restrictions at all. So we have two power series which converge for all values of z. We simply take the e to the power z1 and e to the power, you simply multiply them together. E to the power z1 and e to the power z2, the two series, you simply multiply them together. And the Cauchy product will converge absolutely. The Cauchy product of two absolutely convergent series is absolutely convergent. And it converges to the product. That's the theorem. So all these details you will see in the complex analysis course. In the following, this is the follow-up course. But here we are going to assume all these things. So x to the power m naught is exp of a log x plus ib log x, which is exp of a log x into exp of ib log x. What is exp of a log x? It is simply x to the power a. A is real, mind you. Plus exp of, excuse me, yeah, that's correct. There is a x to the power a into cos b log x plus I times x to the power a into sin b log x. Yeah, right. So there is a exp of a log x into exp of ib log x. Exp of ib log x has been written as using Euler's formula, cos b log x plus I times sin b log x. So that is the, as before, we shall assume that the coefficients of the differential equation a naught, a1, a2 are real. Which means what? The indicial equation is a polynomial with real coefficients. Which means what? The complex roots appear in conjugate pairs. So if m naught is a complex root, m naught bar will also be a complex root. Along with x to the power m naught, you have another solution x to the power m naught bar. So you have these two complex form of the solutions. You take the linear combination with coefficients half and half. You are going to get x to the power a cos b log x plus I times x to the power a sin b log x. You have x to the power a cos b log x minus I times x to the power a sin b log x. If you take the sum and divide by 2, you are going to get the solution x to the power a cos b log x. Similarly, taking the difference and dividing by 2i, you will get x to the power a sin b log x. So corresponding to the pair m naught bar, you can work with the pair of complex solutions, or we can work with the pair of real solutions by taking linear combinations. Correct? Is that clear? So exactly as in the previous setup. So all this comment that I just made has now been formalized in this slide. If you're interested in engineering applications, the constants appearing in the complementary function will be taken to be real. But the problem is that if you write down the solution in complex form and if you want to convert it into real form, then you are forced to take complex coefficients. Take Fourier series. When you work with Fourier series, if you want to write the Fourier series in exponential form, you are forced to work with complex coefficients. So it depends. So if you take complex solutions, then you have to take the C1 and C2 also as complex.
No, these two things are.
You are allowed to take complex numbers as coefficients because the differential equation makes sense over the complex numbers also. So the AJ appearing in the ODE 3.13 are real. So the complex roots occur in conjugate pairs. For the pair A plus minus IB, we get the pair of solutions x to the power m naught, x to the power m naught bar. We're taking linear combinations x to the power m naught plus x to the power m naught bar by 2 and x to the power m naught minus x to the power m naught bar by 2i. We get the pair of real solutions x to the power a cos b log x, x to the power a sin b log x. This is what I just described earlier. Okay. All right, this is all pretty standard. Any questions so far further? What is the next thing to do? What is the trial solution if the differential equation is? Legendre's differential equation. You cannot find a trial solution unless the p happens to be a integer. In the case of the Legendre's equation, Chebyshev's equation, hypergeometric equation and all, we will try a power series solution. We will feed in a power series into the differential equation and try to determine the successive coefficients, get the recursion formula. And if you do this for the Legendre's equation, we get a power series which terminates if p is a integer. And so we get polynomial solutions. But you couldn't have foreseen this without carrying the power series calculation, without computing the recursion formula. You could probably foresee that in the Chebyshev's equation because the clever substitution will transform the Chebyshev's equation to constant coefficient form. Remember yesterday we saw in the quiz that sine of m sine inverse of x, that's a solution. So if m is an integer, odd integer, it has a polynomial solution. But that requires some cleverness to see. But you can, but otherwise you substitute a power series and then you discover from the recursion formula that there is a polynomial solution when m is an integer. When m is not an integer or when p is not an integer, there are no polynomial solutions. You have a proper power series solution with radius of convergence 1. Next thing to do would be to look at repeated roots. Suppose m naught is a root of multiplicity k of the indicial polynomial im. Then what will be the corresponding list of solutions? Once again, you should go back and recall what we did for the constant coefficient case. What did we do for the constant coefficient case? We denoted the ODE simply by Ly, correct? So the ODE is Ly equal to 0. L is a linear operator. What are you trying to do? You are trying to determine the kernel of the linear operator basically, correct? So okay, so what happens when you feed in x to the power m? L of x to the power m is im times x to the power m, where im is the indicial polynomial. Now this is an identity. This holds for all m, real or complex, correct? So what do? This usual trick, the same trick works again over here also. Do the del m on both sides and flip the operators L and del m. You get L times del m by del m of x to the power m equal to the right hand side. The right hand side you are going to get two terms, I prime m x to the power m plus I m into del m of x to the power m. What is del m of x to the power m? Go back to the definition of x to the power m. It is x of m log x. So, its derivative with respect to m is again x of m log x into log x, that is x to the power m into log x, correct. Is it clear? So, the right hand side we get two terms, I m times x to the power m log x and I prime m times x to the power m. But now what do you know about this, and what are we going to do? We are going to put m equal to m naught, and what are we going to do? Since m naught is a root of multiplicity bigger than 1, I m naught is going to be 0 and I prime of m naught is also going to be 0. So, both terms on the right hand side will vanish when I put m equal to m naught. So, again we will get the second solution x to the power m log x when m equal to m naught, right. So, that is what it is written in the next slide. So, put m equal to m naught and note that I of m equal to 0, I prime of m equal to 0 and m equal to m naught. So, L of x to the power m naught log x equal to 0, thus x to the power m naught log x is also a solution of the ODE in addition to x to the power m naught. So, now we have two solutions x to the power m naught and x to the power m naught log x. Clearly I can differentiate again and I can perform successive differentiations k up to order k minus 1, correct, and I can get more solutions. If I m has m naught as a root of multiplicity k, then I m naught equal to I prime of m naught equal to I double prime of m naught equal to all the way k minus 1 derivatives vanish, k minus 1 derivatives of I vanish at m naught, correct. That we saw that yesterday. When a polynomial has a repeated root m naught repeated to multiplicity k, then the polynomial together with the first k minus 1 derivatives vanish at m naught. That is a simple idea that we are using here. So, we are getting a list of solutions x to the power m naught, x to the power m naught log x, etc., x to the power m naught log x to the power k minus 1, and I am leaving it to you to check that these are linearly independent. This exercise has already appeared in the previous list. This exercise has already appeared in the previous list of checking the linear independence of this list of case functions, right. Just write the main points, you do not have to write all the things, I mean it is pretty clear and just write the main points, and because all these things you will be having it in your Moodle eventually, you will be getting it in your Moodle, okay. Just write what the bare minimum that you will need for doing the working out the exercises, and so suppose if k1, k2, kl are the multiplicities of the L different roots, then the sum of the multiplicities must add up to the degree of the polynomial n, which is n, and then we have the full list of n solutions, and it is an exercise for you to check that they are linearly independent, and so you will get a basis of solutions for the homogeneous Cauchy-Euler equation. So, it is completely, so solving the homogeneous Cauchy-Euler equation is completely finished. We have completely dealt with this problem of writing down a basis of solutions of the Cauchy-Euler equation, homogeneous Cauchy-Euler equations, all right. The procedure is very similar to what we did in the case of constant coefficient differential equations, except that instead of the exponential function you are looking at the power functions, that is the thing. And it is also clear why this is happening, because there is a simple change of variables that take the Cauchy-Euler equation to the constant coefficient equation, but then it is better to work out the theory independently, but that transformation gets messy when you want to do the higher order derivatives. You might have checked that. So, what is the next thing in the agenda? finding the particular integral, absolutely. And of course, we have the method of variation of parameters. So, you do have a because you have written down a complete list of solutions for the homogeneous equation. So, now we have the method of variation of parameters at your disposal for finding yp. Okay. So, well, there is nothing much to be said about the method of variation of parameters, we already dealt with it. So, let us look at a simple example, x squared y double prime minus 2y equal to, just write the equation, just write the indices, just write the general solution, no need to, rest of the things you can fill in yourself. So, what is the indicial equation? M into m minus 1 minus 2 equal to 0, and what are the roots? 2 and minus 1, and then the general solution is c1 x squared plus c2 x to the power minus 1, is that correct? Yeah, this is homogeneous. The second example takes up a inhomogeneous Cauchy-Euler. Well, first you have to solve the homogeneous case, for which you have to write the indicial equation. What is the indicial equation for the second example? M into m minus 1 plus 2m plus 1/4 equal to 0. Once again, just write the main equations. I mean, the rest of the things you can write down. Just write the equation, write the roots, and write the general solution. I mean, you can fill in the details. I mean, you have been teaching all these things also. So, the indicial equation is m plus half the whole squared equal to 0. So, the roots are minus half minus half. So, what is the complementary function? C1 upon root x plus C2, roots are minus half minus half, 1 over root x ln x, 1 over root x ln x, roots are minus half minus half. So, C1 upon root x plus C2 ln x upon root x, right, okay. That is the complementary function up there for you. Exercise, this could be a part of tutorial 4 itself. Determine yp using the method of variation of parameters. Apply the method of variation of parameters and find the particular integral. What is the method of variation of parameters? Yp equal to v1 y1 plus v2 y2, where y1 is 1 over root x and y2 is ln x upon root x. And what are the two equations? v1 prime y1 plus v2 prime y2 equal to 0, v1 prime y1 prime plus v2 prime y2 prime equal to Rx. Here what is the Rx? 1 over x squared root x. You have to divide by the leading coefficient, which is x squared, correct? Alright, you can do that. You can carry out the process completely. So, now let us see how the method of undetermined coefficients can be adapted for this class of equations. So, let us write x, instead of x d dx, let us abbreviate, let us use the abbreviation delta. Let us abbreviate x d dx by delta. Notice that x squared d2 by dx squared is delta into delta minus 1. X cube into d3 by dx cube is delta into delta minus 1 into delta minus 2. You can check all these things, the exercise for you. Exercise, check these. Alright. Then how does the Cauchy-Euler equation look like? The Cauchy-Euler equation is x squared y double prime plus 2xy prime plus 1/4 y equal to 1 over root x. So, if you use this delta formulation, how does it transform into? Delta into delta minus 1 plus 2 delta plus 1/4 of y, that becomes the left hand side, correct? If you write this thing in terms of delta, then what happens? It is delta into delta minus 1 plus 2 delta plus 1/4 of y. The right hand side of course is 1 over root x, correct. Shall we proceed? All right. So let us write it in terms of delta. So the equation in terms of delta becomes what? Delta into delta minus 1 plus 2 delta plus 1/4 y equal to 1 over root x, or delta plus half whole squared y equal to 1 over root x. Now you see, is the indicial polynomial staring at you when you rewrite the thing in terms of delta? Okay. So now note that, now what do we do in the method of undetermined coefficients? We have to somehow annihilate the right hand side. Now what is the annihilator of 1 over root x? We are not looking for a constant coefficient annihilator now. We must look at an annihilator which is a polynomial in delta, not d. Earlier we were looking for an annihilator which is a polynomial in d. This time it is going to be a polynomial in delta. So 1 over root x is annihilated by delta plus half. Delta plus half annihilates 1 over root x. So apply 1 over delta plus half to both sides. So here is the yp. So yp is the root of this equation. Yp is the root of this equation, right? Apply delta plus half to both sides. Right hand side is 0, and so we see that yp satisfies a homogeneous Cauchy-Euler of a higher order, third order Cauchy-Euler. What are the roots for this, of the indicial equation? Minus half, minus half, minus half, 3 times, correct? So now write down yp. So what is yp? The full yp, c1 by root x plus c2 log x upon root x plus c3 log x squared upon root x, and then cancel out whatever is there in the complementary function. The first two are already in the complementary function, so cancel them out, right? All right. So what do we get now? Which means, okay, so that's what you get. Yp equal to c1 by root x plus c2 log x upon root x plus c3 log x squared upon root x. The first two terms have been struck out because they already appear in the complementary function. The undetermined coefficient c3 can be computed by substituting it into the ODE, namely delta plus half the whole squared into c3 log x squared upon root x equal to 1 over root x. So work out the algebra step by step. First apply delta plus half to log x squared upon root x, it becomes 2 log x upon root x. Pull the 2 out and apply delta plus half to log x upon root x, you get 2 c3 upon root x equal to root x, or c3 equal to half, and yp equal to log x squared upon 2 root x. The particular integral has been computed. Is it clear? The method of undetermined coefficients can be adapted to deal with Cauchy-Euler equation. Of course, the right hand side is secant x or tangent x. You have no choice but to apply the method of variation of parameters. Method of variation of parameters is heavier, but it is much more versatile. It is a very versatile and very powerful method, and a very superior method. First differentiate and then multiply by x, that is delta. So differentiate, log x squared will be 2 log x into 1 over x, but then you are multiplying by x. So 2 log x upon root x, and there is a second term, and that second term will cancel when you do the plus half, correct. Work out the algebra in leisure, check this algebra and you will get it. And now what is next in the agenda? have lots of fun. Here you are. I am being very kind. I am only giving you 4 problems, not 14. No second page. End of chapter 3. You see that appearing on the last page. Right. So now we will take a small break for 5 minutes.